Okay, let me start here. Okay, any other question? Rimsha, do you have Roshan, do you have a question?
No, ma'am, I wanted to inform you.
Yeah,
as
okay.
well.
Yeah, thank you. Thank you. Okay, so I started it now. Yeah, so basically this is what we were just saying about the number of the levels, code levels that we have here. And B0 is basically our least significant bit, our LSB. It's a term that we will be using a lot. B to the n-1 is our most significant bit. So our VLSB is basically our V full scale, the maximum voltage that we are having in our system or our reference voltage divided by 2 to power and the number of levels that we have. So if on a different operation, how we can find n, it's basically the log to base 2 of V full scale divided by delta. Now, what is the, in the digital, the V full scale is where all the codes is basically become ones of all our digital bits. And this is mapped from to 2 to power n minus 1. Now, how much this is in a voltage level? It is basically 2 to power n minus 1 divided by 2 to power n levels multiplied with the V full scale. It's basically, this is the delta. So it's 2 to power n minus 1 multiplied with delta. And this gives me, sorry, no. Yeah, it's basically gives me a V full scale minus delta. So I won't be able to map my reference voltage. I will have my minimum maximum code is basically maps to a VREF minus delta. And this is because I am starting from 0. Okay, any question on this? Okay, now this, the voltage level where basically I change my code, we call it an input trip level. And as we discussed, as much as I have more, as I increase the number of codes that I allow, when my resolution of ADC increase, then I will have a lower or a less quantization error. And as you can see here, if I have for the same sinusoidal input signal, let's assume it here. Yeah, if I have just 1 bit of quantization or 1 bit ADC, I will be able to just map into 2 levels, which is either 1 or 0. So you can see I will definitely have a huge quantization error here. As I increase my number of levels, I will be able to mimic the original signal and reduce my quantization error. Here, I mean, I still have a quantization error, though it looks like it's a continuous signal or a pure sinusoidal, but it's not. In reality, there is still some, if you zoom in, you will find the quantization problem or error. Okay, now if we want to look at it from a mathematical point of view regarding the quantization, it's a quantization error, but usually it's known as quantization noise, though the noise is basically, we assume it's a random thing or a random signal, but the error is a deterministic function of the input signal, but usually it's known as quantization noise. So in the low resolution ADCs means less than 6-bit, this quantization error usually appear as a distortion component. Why? Because basically those quantization error is more of a function of the input signal. So it depends on the shape of your, or a type of your input signal, and therefore it is going to appear in your output spectrum as a distortion, which is basically another harmonic. So if your input signal, let's say a sinusoidal signal at F0, after you go into this ADC, the output will not only have this F0 signal, but you will have another distortion components that they appear at F1, which is, let's say, 2 of F0, 3 of F0 at the harmonics of the input signal. And this is basically when your distortion or quantization error is a function of your input signals. And that's something not desirable. Now, when I increase my resolution of my ADC, so my N is greater than 6 bits, this quantization error, now I have a larger number of levels, and my quantization error is not anymore a function of my input signal, but I can assume it as uniformly distributed between minus half LSB to half LSB. So it will look something like this here. So this is minus half LSB or minus half delta to half delta, the maximum value that and the minimum that it can take. So it's well uniformly distributed between those two values. And therefore, I can assume it as a white noise in my bandwidth or my interest from 0 to half of the sampling frequency. Now, again, from how I'm going to compute it mathematically, if I assume my input signal is a linear a ramp signal, this is in the green, therefore my quantization error will appear as this sawtooth wave between minus half LSB to half LSB. So I can find the root mean square value. How I can find my root square RMS value? First, I will square my signal. So I find the square of my signal. I will find the mean by integrating. So first you find the square or square your signal. Square the signal. Then find the mean. How you find the mean? By integrating and then dividing by the period. And the third thing is that you are going to find the last thing, find the square root. So this is how you're going to find the RMS value. So once now, if you look at this, so it's going to continue. I mean, my drawing is not so accurate. I draw it. This assume that it's connected here, and this is minus T over 2, and this is T over 2. So it's a complete one cycle, which is 1T period. And I am integrating from minus half of T until half of T with the VLSP minus T over T. So in this period, it's just a linear function with a negative slope. And then we are integrating it and finding the square root. So this will gives me basically, if you do the math, you will get the root mean square value is the value of this LSB divided by square root of 12. Now, if I do another from a stochastic point of view, and again, as I assumed my quantization error is uniformly distributed with the probability density function, PDF is basically a uniformly distributed from minus half LSB to half LSB, and this height is basically 1 over V LSB, because if you want to, now this is the property of the PDF, if you integrate it over time, you get 1. So this has to have the height of 1 over delta. Now, in order to find the root mean square value here, you need the x squared, you square the signal, multiply it with the PDF probability density function, you integrate over the from minus infinity to infinity, and then you find the square root. Again, you do the math, you end up with the same value that we got earlier. And this is important, you need to know this value, that your quantize or the RMS value of your quantization error is basically V LSB divided by the square root of 12. So this is an important thing that we need to know. Okay, now why it's important for us? Hamza, you have a question?
Yes, ma'am. Actually, I was asking that these two approaches, deterministic approach and stochastic approach, we are trying to find the quantization error in case we have bit n is greater than 6.
Yes. Yes, so we are finding what is the RMS value of the noise for basically here, these are the cases when we have a larger number of bits, they are greater than 6 bits. Because we said for a lower resolutions, they will be, we cannot make this assumption, they will be the quantization noise will be a function of the input, and therefore it will also generate distortions that. So here we are assuming that it's uniformly distributed with when n is greater than 6, and that's the most of the cases that we will be using. So we don't need a very low resolution ADC. We usually need like 10 to 14 in many applications. If you need a higher resolution, you will even go to 20 or more number of bits. So the lower resolution, they are not of very much, let's say, high demands or application wise. So we are focusing on the larger numbers. And why do I want to find the RMS value of the noise? So I can find some important quantity to identify the quality or the performance of my ADC, which is the signal to noise ratio or signal to quantization noise ratio here. So, you know, I'm sure you have heard of the SNR, or now the SQNR is signal to quantization noise ratio, and basically it's 10 log of signal power over quantization noise power. Now, if you convert it into a voltage domain, then it will be the square will come out from inside and goes to outside. So it will become 20 log of V signal RMS over noise, quantization noise RMS. Now, if we want to find the signal power or the signal RMS value, assuming that you have a sinusoidal signal that basically have the amplitude goes here basically from 0 to V full scale. So this is the A of it will be equal to V full scale divided by half. So now the signal power on the V full scale is basically equals 2 to power n multiplied with the LSB voltage. So now the signal power one second, just give me. Yeah, the signal power is basically A divided, or this amplitude A divided by 2. And the RMS value is this A, so this A square. A divided by square root of 2. So it is square root of this signal, assuming that the signal is basically periodic. It's a sinusoidal signal. And therefore, so if I plug in here the signal power square, so the same the A, which is 2 to power n multiplied with the V LSB divided by 2, divided by 2 that I brought it from here. So now this is my signal power. The quantization noise is the RMS square. Now you remember that the RMS was VLSB divided by square root of 12. So I plug in these values here and you will get this relation. Now we can simplify it further. And we get to this very important relation here. So what is this relation tells us? I mean, this is coming after you open the log function here. So you will get that SQ1R is basically 6.02 multiplied with annual resolution plus 1.76. So here, what does this relation tells us? That I will be able to get SQ1R that depends on my resolution or of my number of bits of my ADC. And that's something very important when you want to design for a certain type of ADC. So it will tell you how much you should expect. If you design for 10-bit, you cannot assume that it will give you, let's say, 100 dB SNR. So this will gives us a performance metric or a design process for our ADC, what to expect in terms of SQ1R performance according to the number of bits. Any question?
Ma'am, with this
Yeah.
formula, we are measuring the performance of our DAC to ADC
Yes,
for the designing of ADC.
yes. Yes, what is the question?
I just want to confirm that thing.
Yeah, okay. Now, I'm not going to take questions from chat. Please ask your question directly. It's difficult for me to read and see the slides. I have only one screen. No question. Okay, then I'm moving forward. Okay, so now this formula gives us very good results, especially for high resolution ADCs. Now, if we compare basically the simulated SQ1R with this formula, so this means that the simulated that I designed an ADC and I simulate the maximum SQ1R that I can get from it and compare the value according to this formula for basically this resolutions. You can see that when the resolution increases, the error between the estimated value of the SQ1R with the real that I got it from simulation, you can see very small errors comes at higher resolution. So this basically gives us a very good estimation. Now, when I go to higher resolutions further, now the problem becomes that I am not dominated by quantization noise anymore. There are other types of noise that comes into play, and this is basically an important one is the flicker noise or the thermal noise. What is the thermal noise? Anyone have heard of it? Basically, now all my components, which I use them to implement my ADC, they have noises. So there is a noise that comes as a part of my design. So for example, the capacitor, it gives you a noise. The resistor as well, it gives you a noise. Transistor themselves, they also have a noise. So now the quantization, why at higher resolution, I become more limited with the thermal noise as compared to the quantization noise. So let's say at lower frequency, I have quantization noise. More dominant, while at higher resolution, let's say above 14 bits, here basically the dominant, what we just saw in this slide, that quantization noise dominates up to around 14. Now, after that, basically it comes the other types of noises. Thermal noise, you have 1/f noise if you work at the lower frequencies. So why do you think this happens? Any idea? No idea. Okay, basically, just let's think about the thermal noise and 1/f noise, it's always there. Okay, whether I work at a lower resolution or I work at higher resolution, it's there. I can try to reduce it with a certain design techniques, but it's there. Now, what's happening to quantization noise? Quantization noise, what's the difference between being at lower resolution versus higher resolution? I mean, this thing we have said. What is the difference between quantization? Where is the quantization noise more? Is the quantization noise more at lower resolution or at higher resolutions?
I think at lower resolution, quantization error can be more.
Yes, definitely. At lower resolutions, because you have a lower number of levels that you can cater, then you will have a more quantization errors. But once you go to higher resolutions, then you have very small delta that you basically cover very large number of levels. So your quantization noise significantly drops. Therefore, the thermal noise, which was already there all the time, it becomes more dominant because I have significantly reduced my quantization noise. Now look at this table here. It's showing you how the resolution is changing, and 2 to power n is the number of levels that I can support. So if I have a 2-bit resolution, I can have only 4 levels. And if I have 10 bits, then I will have 2 to power 10, which is around 1000. It's 1024. If I go till 20 bits, I have million levels, or more than 1 million levels. And you can see that how much that significantly going from lower resolution is exponential increase, 2 to power n increase in the number of levels. And therefore, your delta, here basically the third column is showing you the delta value in terms of voltage, assuming that your V full scale is 10 volt. I mean, this is a very, let's call it old assumption. Nowadays, you work at a V full scale of 1 volt and below. So if we divide even this value by 10 to have a V full scale of 1 volt, so this all going to be divided by 10, all these values. So you can see that, I mean, with the increasing, we certainly at 20 bits, so our delta will be 1 microvolt, which is very, very low value, 10 to power minus 6. So therefore, you can imagine the advantage that I am getting in terms of reducing my quantization noise. Now, therefore, the thermal noise becomes the more dominant because let's say it's if you have a constant value, let's assume, just make something that's a constant value of the thermal noise, while your quantization noise significantly drops with your increasing your resolution. And therefore, this is the dominance that we are talking about it here. So that's a part when you will basically be designing, you will need to know who's more dominating and how to, so you use the proper techniques to reduce these noises. Now this is showing you the number, the percentage versus V full square. So if I have, as we just said, 2 to power 2.5 divided by 10 volts, it's just 25% of your V full scale. And this is the part per million. So just multiplying it with the percentage with 10 to power 6. And dB full scale means that it's basically how much dB difference between this value and the V full scale. Okay, so in the most practical application, our input signal to the ADC is a band of frequencies plus some noise. So it's not just a single frequency, it is a band of frequencies. For example, if you work on EEG signal, your input, your band of interest lies from millihertz until, let's say, 100 or 70, I think 70 hertz. So this is your all band of interest. Beside that, you will have also other higher frequency noises. Okay, so the quantization noise, therefore, is basically considered to be a random white noise that is uniformly distributed between 0 and half of our sampling frequency. Now, and why we are keep talking about from 0 to half the sampling frequency, basically the way that we will see also in the future lectures, the way we study and the ADC performance, or we judge the behavior or the functionality of the ADC. An important way to understand it is to look at it in the frequency domain. That's something very important, and you will see it on all of the ADCs. You should, basically, you cannot see any paper describing an ADC without showing the power spectral density of the ADC, or the FFT plot, the spectrum of the ADC output. That is a must, because it's the way that you can judge the performance of the ADC. And that's why it's important for us to understand it and study this, how to interpret the power spectral density of an ADC, and be able, just by looking, to see, okay, is it a good ADC or it's a bad ones? And that's what we are going to see by time through this course. Now, when you want to, so we said in the real life, my signal is not just one frequency tone, it's a band of signal or frequencies. But when you want to test the performance of ADC, or you simulate it, or you measure it in the real life, you basically bring one sinusoidal signal of a single tone, and you inject it into your ADC, and then you measure the output. Why is that? Because you know that the sinusoidal has a one tone frequency at minus F0 and F0, but we look at just the positive side of the spectrum. Okay, so it has a single tone frequency, and then you will see multiple things at the output. And those things that you will see at the output, they will be able to tell you how good was your ADC design, what are the errors, and how you should fix them. I mean, that's come by time of experience. Okay, now when you want to select the frequency of this sine wave, it's not a random thing that you will do selection. I mean, if you make a wrong selection, you might be mistakenly think that your ADC is not doing good, while in reality it can be a good design. But if you select a wrong frequency of your input test signal, you might end up seeing issues that they will not be there in the real life when you will test it on these band of frequencies. And now I'll clarify that furthermore. I'm just going step by step here. So this is basically, if you apply something wrong and see obviously a wrong behavior of the ADC, this is called a testing artifact. Means it should be that we should avoid doing this, applying a wrong signal, because it will basically give you let's call it illusion that your behavior or your ADC is not doing the right thing, while in reality it is. Okay, so it will mislead you, this giving a wrong signal. Now, what is this? Sorry, what is the definition of a wrong signal here? If you apply a test voltage, a sinusoidal signal with a frequency input of FA, and your sampling frequency is FS. If your FS divided by FA is an number that is a power of 2 here, or sorry, it's an integer number, then this is going to give you a wrong behavior. Now, why is that? If this is my input signal of FA, and my FS is basically integer multiple of FA. So for example, every time I will be sampling my signal in every cycle at the same points. So every cycle of your sampling frequency, your sampling signal will sample your input signal at exactly the same location, because it's just an integer multiple of it. So let's say if 5 times your input signal is 1/5 of your sampling signal, we will keep on sampling the input signal at exactly the same location every single cycle of your input signal. Is that making sense?
Ma'am, can you repeat it a bit, ma'am?
Yes. If my sampling clock is an integer multiple of my input signal, what's going to happen is that you will sample your input signal at exactly the same locations. So for example, this is my input signal and I am sampling. So in this cycle, I will sample here, I will sample here, sample here, here. So in the next cycle, I will exactly sample at the same locations here, here. I mean, my drawing is not so accurate, but this is what's going to happen. Will happen the same here, will happen the same here. So I will sample at exactly the same location every time. If that part is clear. Now, what's the problem of doing this? What's going to happen if I do this? Why it's a problem? Why? Because every time I will have the same error, quantization error values. Okay, again, so if I sample at exactly the same location, this means every cycle will give me exactly the same error that I have seen in the previous cycle, and so on, so forth. All the time, it will continue to happen this problem. Now, why this is again a problem if this happens? This means that I am not going to have a uniformly distributed error. The error will be only a certain values. So not well distributed between minus delta LSB and minus half LSB to half LSB. It will be only taking a certain set of those values. It's not uniformly distributed. And if this happens, then it is a function of the input signal. The error is a quantization error is going to be a function of the input signal. And this means that it's going to appear as distortion in my spectrum. Is that making sense to you?
Ma'am, I didn't understand this thing that if the sampling is exact at the same position in every cycle,
Yes.
then how can be this quantization error is not uniform in every cycle? How is that possible?
It's not, it is, the quantization error will be same values every cycle. Yes, you agree?
Yes, but what does this mean of uniform distribution? What is the meaning of uniform distribution?
The meaning of uniform distribution that it take, let's say this is minus half LSP to half LSP. It takes, I mean, it covers all this range equally, let's say. If I have the same value of error, let's say I get minus LSP over third. So it will, this value will have a more value than anybody else in the range. So it's not uniformly distributed because the error is same values keep coming. So it's not taking all the values within this range, minus half LSB to half LSB. It's taking certain values of it, not covering the entire range.
All right.
Got it?
Yes.
Okay, now again, if this happens that it takes certain values, means it's not uniformly distributed, means it is depending on the input voltage, it means that you will have harmonic distortion in your FFT spectrum, in the output spectrum of your signal. Now look at this example here. If I have my Fs over FA, so it's an integer multiple of it, and the value ratio between them is 32. This is my input signal, is coming at what is this voltage? Maybe I'm not sure. Maybe this is 100 hertz. Just let's assume it's 100 hertz. Okay, you can see this is the original signal, the FA. Now you are seeing at 200, 300, 400, and 500. Assume that this is the correct x-axis. So these all are harmonics. The integer multiples of your input frequency, if they have a larger value of your FFT, these are called harmonics. Okay, and these are undesirable. We don't want them to have them because these are considered as noises in my signal. So they will decrease my SQ1R. Because when I find the SQ1R, this is the signal power, the 0 dB here, and the sum of all these noises is going to be the noise power, and the ratio between them is the value of SQ1R. So if those goes to higher values, this means they have more noise, and more noise will means my SQ1R will be more reduced, and this is something that I don't want it to happen. Now, if in this other side here, if I have this ratio that basically my sampling frequency over FA is 4096 divided by 127, which is not an integer number. You can see that now these harmonics is basically have been eliminated. I mean, you just have this noise floor here, but not the harmonics. And this is more better performance. Now, this is at the block diagram that you see up here is basically how we are going to have the testing of the ADC. So you will have apply an input signal of a frequency FA. You will apply it on the ADC, and then you will store the output in a memory of words, and this depends on the points of the FFT processor. And basically, since we are just interested from 0 to half of the V full Fs over 2, then we are taking only half of the output of the FFT, the other half from Fs over 2 to Fs, it will be a redundant and just the same thing. So it does not give us more useful information. Okay. Any question? Is this clear? Okay, now this one performance metric, which other than the SQ1R, is basically called SFDR. SFDR is Spurious Free Dynamic Range. It tells you in dB the difference between your input signal, the input signal, and the maximum harmonic, the highest harmonic that you see in your dynamic range, in your spectrum. And this tells us also as the large value of this signal is, or this high value of SFDR is basically a good thing. And we will see how it's also related to other performance of the ADC later. Now, if I want to interpret the output spectrum of the ADC, so basically you will have the largest tone or is going to represent our input signal frequency. Now, if you remember this relation. So if my input signal is basically coming at, let's say, a 0 dB level, why my noise does not come at 74, minus 74 dB? Why it comes at minus 1.7 dB? I mean, based on this relation, the SQ1R, it's the noise signal power. So here 0 dB minus 74 dB minus 74 dB, and this is the 74 dB that we are getting by considering 12 bits. So why if my signal level at 0 dB, why my noise floor is not at minus 74 dB? Why it appears at lower value? Why it appears at minus 107 dB? The reason behind this is basically because when you calculate the noise power, you don't find a single value for the noise. You sum up all these noises that they are here. So the minus 74 basically noise level is the sum of all these values. It's not a single value of the noise, and that's why your noisy floor basically appears at a lower level, because your total noise is summation of all these noises. So the share of each of those frequency bands of my ADC, my FFT output, is basically the total noise divided by the number of bits or the number of points of my FFT. So this means that if you have a larger number of FFT size, this means your noise floor will go further down. Is this means that it's going to change your SNR value? Will it change? My question, will it change the SNR value if I have a larger FFT size?
Ma'am, quantization noise level is at the same. So I think so that wouldn't be changing.
Yes,
Maybe.
Exactly. It will not, though the noise floor is going down, but it's not going to change my SQ1R. Why? Because again, whenever I'm going to find the noise, I will sum all these bands power, the noises together. So it's like I have the same amount of noise. If I am distributing it to, let's say, 64 point FFT, I will distribute it to 64 bands and they will have a higher level. If I'm going to this by, let's say, 1024 FFT, they will go at a lower level. So the average will be lower, but the total amount will stay the same. And that is basically the difference. Now, why I am going then basically, if I'm going to use a larger FFT size, this means that I am going to need a larger memory, more computation, and if it is in simulation, it will take me days to finish maybe these simulations. Why do I want to do that? Why should I, if the output is the same, why should I then suffer and have a larger number of FFT points? What is the advantage of doing it? The advantage basically is that what if I have some harmonic here? Okay, that's coming because of bad thing in my system. Now, if I have a lower point FFT, this harmonic will be hiding within this high noise floor level. if I reduce the quantization errors, the noise floor level to that's caused by quantization down with a higher FFT, I will be able to see this harmonic and know that there is something wrong in my ADC that I need to fix in my design. So that is the advantage. Okay, is that clear?
Yes.
Okay. Now let's talk a little bit more about finding the FFT. I think this is just basically ideally a revision for you. I'll give you a MATLAB assignment similar somehow to those stuff so that you can revise how you calculate the SNR and all these things from the MATLAB code. I'll give you the code. You just need to run it and understand it and report the results. So basically, the DFT tells us that what is the spectrum of a signal. It tells us the frequency content of the signal. So ideally, if I have an input, one input or a single tone that sine signal that I am applying at the input of my ADC, I should expect that I am also getting a single tone at the output of my ADC, but that is not the reality. That does not happen in real because these are not ideals. So you will see other frequency content of at the output spectrum, and those they will tell you information about the performance of your ADC. So we typically are interested in the frequency range from 0 to fs/2. And we apply the FFT to our output spectrum, and we see the performance, and we usually normalize it to the V full scale. So it will be starting from the maximum value that you will be having is a 0 dB. So this is an example of a MATLAB code that's normalized. So your sampling frequency is 1 megahertz. Your input signal is 50K. So now our N or number of FFT is 100. We usually prefer to have, in order to have FFT, so this is discrete Fourier transform. If you want to have FFT fast Fourier transform, you need to select N to be 2 to power of something to power of 2. So 64, 128, and any number of 2 to power something. Okay, so now if my input signal is a cosine signal having amplitude of 1 and input frequency of fx, and then I find basically the 20 log of the input signal, and here basically you do the absolute dividing by the maximum value square and over n, you get the maximum value at the input signal is of a 0 dB. And then we drop the redundant half because again, we are interested from 0 to half of fs. And then this is your x-axis that they are converting it into normalized x-axis. Now we have a sinusoidal signal of only one frequency. From where this noise floor has came? What is the source of this noise floor? Any idea? Does MATLAB use a quantized signals or they use a continuous signals? What do you think? MATLAB is a computer program. So does it have infinite number of resolution or it has a certain resolution?
Ma'am,
It
limited
should
number.
have yeah, it have a limited resolution. What does this mean? That there is going to be a quantization noise. I mean, you can see it's a very low value of quantization noise, minus 300 dB, but still there is a quantization noise of MATLAB because it's a computer program. It has a limited resolution. It's not an infinite resolution. And therefore, the source of this noisy floor is coming from the quantization noise of the MATLAB, that limited resolution of the signal. Okay, now I have another signal here that I basically apply the DFT of it. It looks a sinusoidal signal in the time domain, but when I applied it, you can see what happens to this FFT. It looks too bad. I mean, where the signal bend is barely visible. What's wrong here? Basically, in MATLAB or in the DFT, it assumes that whatever input signal you are giving to it, it's a periodic signal. It takes this assumption that your input signal is a periodic signal. So this part which was given here, it will, I mean, assuming that it's being replicated every time. Now, you can see now if you connect this part here to the other part here, they will not match each other. There is some discontinuity that we are seeing here. Now, this discontinuity in the time domain, it will turns into a problem in the frequency domain that we call it a spectral leakage. Basically, the signal power does not come into a single frequency band, but it leaks to other bands around it. And that's a problem, does not give us the real picture. So how can we solve it in the when we want to perform the DFT function? You have two solutions. Either you select an integer multiples of the number of cycles. So therefore, if it is an integer cycle, complete cycle, then when you will connect it every time, it will be a complete periodic signal. Or we can do another solution which is called windowing. I hope that you have heard of these things in your signal and systems course. So now if you have an integer number of cycles, you can see if I connect this part to this part here and assume this signal is going to be end up in a periodic signal. And if you find the FFT, it will look good. I mean, you will have the signal power into one tone. Now, if I have a non-integer number of cycles, you can see that the signal, you have this problem of the spectral leakage. So now this is how you can see it in the MATLAB. You basically select your sampling frequency and the number of cycles to be 7, which is an integer cycle. So you make this basically choice that to have an integer number of cycles, and this will gives you a proper output spectrum. Now, if in some cases you cannot basically apply, just you need to make sure that you also, again, have the other previous condition that the number should be basically, number of cycles should be integer, but it should not be, sorry, the number of cycles, yes, should be integer, but your s over fx also, we said that our input signal, they should be a non-integer number. Otherwise, basically, we cause that issue of the quantization noise that this will not be properly distributed. Okay, now, again, this is the same similar example. Now, there is another solution, we called it windowing, and that's more, you find it more practical because sometimes it's difficult on testing to make sure that your input signal is same or aligned to your sampling frequency. And therefore, we go to the other solution, which is windowing. Windowing is basically we multiply our input signal with a window function. Now, we multiply it in the time domain, which means it's a convolution in the frequency domain. So the windowing basically what it smoothes out the edges of your input signal in order to somehow make them zero. So once you will then map them to next to each other, they will be looks like a continuous signal. So you have this is before windowing. You can look at the spectral leakage problem. After windowing, we sorted out the issue. However, the signal might not be just on a single bin. It might be coming on a more number of bins. So you have a choice of multiple window types. You have, and each one of them have a difference between basically, if they are more wide in the time domain, in the frequency domain, they will have a more narrower bandwidth. So based on the application, you can select them. So again, it's integer multiples of cycles is a good solution for the simulation. However, when you do a real measurement testing, sometimes it's hard to do that, selecting the number of cycles versus selecting the frequency of your input signal and your clock frequency. So you go to the choice of windowing. And this is basically an example of doing windowing. So again, here the signal bin came at this value. So this code shows you how to calculate the SQ1R. So basically the signal, we found the signal bin. And here this is you found the power that is at the signal bin. And then any other pin within the range is considered as a noise. Therefore, in order to find the noise power, we find the sum of all those other bins of the signal except the signal bin. And the SNR is the difference between the signal power and the noise power in dB. Okay, again, here you can see that if you have an SNR of minus 62 dB, why your noise floor does not appear at minus 60 if your signal is starting from 0. And this is again because of that this noise power is distributed across all the bins of the FFT. And you need to make sure when you plot in the FFT, you need to mention how many number of points that you have used, because the number of points will shift your noise floor by this amount. So I just want to show you this example that if we use with, is it this one? Yeah, if I use with this 4096 FFT size, you can see that you have this noise floor at this level. It's almost at minus 90 dB. But I cannot see, I mean, this is a very, it's a harmonic, but it's not quite visible. Now, if I increase my FFT size to 2 to power 16, I think this number, you can see that the noise floor has reduced significantly. And now this harmonic is quite visible. So therefore, I know that I have, let's say, a third harmonic that is in my system. So I need to go back to my design and check what's wrong, why this harmonic is quite large. Now, this is basically was just a quick review. I mean, you should be knowledgeable about the FFT already. So sometimes we intentionally add a noise. And this is basically, for example, a case if you have an input signal that is a DC value. So it's a constant value. Now, if you apply this constant value in your ADC, what again, I mean, that should be clear to you now that you will not have a uniformly distributed error because you have a fixed value of error that's every time coming the same error. So you will not get a uniformly distributed error. You cannot make those assumptions which we made earlier. So what you do is that you intentionally inject a random noise with your input signal, as you can see here in the red. in order to get a uniformly distributed error. So this has an applications if, as I mentioned, for example, if your input signal is DC and you want to test it, so in order to not to be misled by that your error is not uniformly distributed, so you can do this thing. And if you are interested to know more about it, you can read this article. And I think we are done here for today. If you have any question, please ask. Yes, any question?
Ma'am, I have a question.
Yes.
Ma'am?
Yes. Yes, I can hear you. Please go ahead.
I have a question about the virtual lab that you have sent to us.
Yes.
So they're saying that VMware or some other software is to be used for hosting the virtual machine for labs. So
Yes.
do we have to download that software before we download the machine?
Yeah, I mentioned that you should ask the TA basically regarding all these details of installing the labs.
Also, ma'am, I wanted to ask, will you be sending the code files to us so we can test them for ourselves? These codes
I
that
will
you
not
showed
be,
us.
I will be sending the code, but you have to write the code. I mean, you have to type the code yourself. And then